My name is Anna Jungblut and I'm studying for a PhD in condensed matter physics. So my research is focused on studying solar cells, and more specifically I work with a specific type of solar cell which is called an organic solar cell. And what that means is we use organic molecules that have carbon and hydrogen in them to make solar cells out of. And ultimately my work is focused on exploring different types of materials and specifically looking at fundamental processes to explain why solar cells work the way they do and how we can overcome current limitations and make them better. Traditional solar panels that we see on roofs at the moment are mainly made out of silicon, and they're amazing because so far we've been able to get them to be quite efficient, probably around 25% efficient from converting solar energy into usable electricity for us. But one of the main constraints with traditional silicon solar panels is, number one, it's quite an energy-intensive process to get the silicon to be pure enough to make a good solar cell. And in addition, silicon is quite crystalline and heavy, so a lot of the modules that we put on roofs, we need to make sure that we reinforce our roofs before we can install them, which is adding an extra hassle and point of cost to the installation process. And so a lot of people are looking at alternative materials such as novel perovskites or organic solar cells because they have the potential to be made a lot cheaper and a lot lighter, even if they're not as efficient as silicon solar cells are at the moment. And so if I show one of the solar cells that I have made, so you can see that they're basically transparent, which is obviously not what we traditionally want from a solar cell, but this actually opens up a lot of interesting avenues to make semi-transparent solar cells that we can use to coat our windows and phones with and use currently unusable space that we wouldn't be able to use silicon solar cells for. And so the idea with a lot of the materials that I work on is that eventually when we get our fabrication and commercialization capabilities up to speed, we're going to be able to print solar cells like we print newspapers, which would then also bring down the cost quite substantially and make this a really affordable renewable energy resource. Organic solar cells are not as efficient as commercially available silicon solar cells, and part of my research is actually about exploring why that is the case. And so some of it could be related to fundamental processes that occur in organic molecules but that don't occur in silicon. So at the moment, the best organic solar cells that have been made in a lab, not my lab, but in a lab, are about 17% efficient. And commercial silicon solar cells are about 25% efficient. Now, this might not seem like a big difference, but we have fundamental thermodynamic limits that mean no solar cells can be more efficient than 33% unless we employ a few little tricks, but that's sort of the upper limit of what we can reach. So silicon is actually really close, and organic solar cells are getting closer to that, but there's still a little bit of research left to be done. Now, if you ask me how efficient the solar cells are that I make for my PhD, well, some of them are maybe 2% efficient, some of them are maybe 0.5% efficient, but the main thing that I'm looking for is not to make the best possible solar cells, but to explore fundamental processes and the fundamental physics of the materials that we work with to inform ultimately industry, and they can make the high efficiency devices. My day-to-day research usually starts in this lab using the tool that is right behind me, which is a thermal evaporation system. And I use it to make my solar cells, and that takes about 4 or 5 hours usually on a good day. The way we make these solar cells are, we start off with little pieces of glass that are about 3 by 3 centimeters long and wide, and we pump these into our thermal evaporator. So all of this is put under vacuum. And then we have little boats, ceramic boats that look like this, that we fill up with colorful materials. And once everything is under vacuum and in a safe state, quote unquote, we start to heat up the little boats and the materials start to evaporate inside the chamber. And then we have really fine control over how thick we want specific layers to be. So the materials would start evaporating and start condensing onto the glass that we put into our evaporation system. And then we can really fine tune how thick we want the layers to be. So most of my devices are not thicker than 100 nanometers maybe, so they're really quite thin. And it's a quite repetitive process to start with material 1 and then material 2 and material 3 until you have the full stack of what makes up a solar cell. Once we have made the solar cells, I take them back into the glove box where I handle them in a nitrogen environment, because a lot of the materials that we work with are not stable in air or light, which is not great for solar cells, but part of our research is trying to figure out how to circumvent some of these issues. But what I need to do then is I need to print a little bit of glue on another glass slide that I stick on to encapsulate my solar cells, and then I can take them out to various different labs in the area and I test them, sometimes by varying the temperature and seeing how the solar cell performance changes as a function of temperature, or by shining lasers on them and studying what happens. In 10 to 20 years, I would be very surprised if we didn't see silicon solar cells at least on almost every roof. But what I'm really hoping to see is that some of the new materials that we're working on at the moment, be it organics or other types of materials, will have made it to a commercializable state, and we will actually see different types of solar cells all around our cities. And one of the things I'm looking forward to seeing is to see solar cells being integrated into buildings, in the windows, possibly on your phones, so that you can harness a lot more of the solar energy that we're currently not making use of.